bridges the conceptual design with practical implementation.
Objectives. At the end of this session, you will be able to construct a single-stage transistor amplifier using simulation software and construct the prepared circuit into a layout diagram using simulation software. Parameters of the PCB layout. PCB has many parameters. They are mils, traces, trace width, annular ring, minimum ring width, minimum clearance, routing layers, and routing topology. Mils. Every feature or detail you design for your PCB must be at least 6 mils or 0.006 inches in size for the PCB fabrication process to produce it reliably. Attempting to reduce the size below the designated mils could lead to mistakes or discrepancies in the final PCB. Traces. Traces are the conductive pathways on a PCB that link various components and enable communication and cooperation between them, much like the wiring in a house. Traces width. The thickness of the conductive channels that link electrical components on a printed circuit board is called trace width. A broader trace offers lower resistance for improved signal integrity and can carry higher currents without overheating. Selecting the right trace width is essential for creating a dependable circuit that satisfies electrical requirements while considering manufacturing capabilities and space restrictions. Annular ring. It is the annular space that exists between the closest copper feature, such as a trace or plane, and the edge of a plated through hole or pad. To maximize solder joint quality and avoid soldering errors, designers set the dimensions of the annular ring. Minimum ring width. The smallest permitted annular ring width surrounding a plated through hole or pad is known as the minimum ring in PCB design. This is important because it guarantees the dependability of the solder bond and electrical connectivity. Minimum clearance. It refers to the smallest allowable distance between two conductive elements, crucial for preventing electrical shorts and ensuring signal integrity and reliability. Routing layer. These are conductive layers used to route the traces between components. Multiple layers allow for more complex circuits, minimizing signal interference and providing better routing flexibility. Routing topology. It means arranging and connecting traces on the PCB. Common topologies include point-to-point, star, and bus routing, each with advantages in terms of signal integrity. Next, we will look at the construction of a single-stage transistor amplifier. For this, you will need the following tools and equipment such as personal computer and simulation software installed in the personal computer. Now let's see the construction of a single-stage transistor amplifier. The steps involved are: Step 1. Construct the single-stage transistor amplifier. Step 2. Run the circuit using the simulation software. Step 3. Convert the prepared circuit into the layout diagram. Open the simulation software that is pre-installed in the PC. Before opening the application, run as administrator for accessing all the library. Click on New Project to construct the circuit diagram. Name the project. Here it is saved as the single-stage amplifier. Click Next to proceed. Select Create a Schematic and continue with the default mode. Click Next to proceed. After selecting all the layouts, click on Finish. Refer to the circuit diagram to place all the components on the schematic capture. According to the circuit diagram, we need the following components. Type transistor BC547. Click OK. Type capacitor and select electrolytic capacitor and click OK. For placing the same component, right-click on the mouse. Place two other capacitors. Type resistor and select RES40 and click OK. For placing the same component, right-click on the mouse. Place four other resistors. Common ground, signal generator, and oscilloscope. After selecting all the components, place them according to the circuit diagram. Go to Virtual Instrument mode to select both the oscilloscope and the signal generator. Now click on the Terminals mode to select the common ground. Wire the components according to the circuit. Now we can assign the values to each component. Now assign the values to the resistor and capacitors accordingly. Right-click on components and select Edit Properties and change the value accordingly. Use Ctrl+E for shortcut. Fix the values of each component as follows. R1 is equal to 100 kilo ohms. Click OK. R2 is equal to 100 kilo ohms. Click OK. R3 is equal to 10 kilo ohms. Click OK. R4 is equal to 10 kilo ohms. Click OK. R5 is equal to 1 kilo ohms. Click OK. Capacitor C1 is equal to 10 microfarad. Click OK. C2 is equal to 10 microfarad. Click OK. C3 is equal to 10 nanofarad. Click OK. Move on to the generator mode to give the DC voltage to the resistor. Apply 12-volt DC supply to it. Now the circuit is ready for converting it to the layout diagram. Click OK. Conversion of the prepared circuit into layout diagram. Now navigate to the PCB layout for conversion of the circuit. Right-click and a new tab will open with the name PCB Layout. Click on the board edge to draw the 2D graphics box mode. Let us convert the prepare circuit into the layout diagram. Click OK to proceed. Click on Tools. Select Auto Placer to select the components of the circuit. Select all the components. Adjust the placement grid and edge boundary accordingly. Click OK to proceed. After clicking OK, all the components will be placed on the layout. Adjust all the components as per the given circuit. After arranging all the components, click on Design Rule Manager and navigate to Net Classes. Select the wire type as through-hole and click OK. Navigate to the top right and select Auto Router. Click on Begin Routing. Click OK to proceed. Now we can see the layout diagram of the constructed circuit.
This brings us to the end of this session. In this session, we have learned to construct a single-stage transistor amplifier using simulation software and construct the prepared circuit into a layout diagram using simulation software. Thank you for watching. We will see you in the next session. Hello and welcome to this session. In today's session, we will delve into simulation of a simple electronic and power electronic circuits using LT-SPICE. This simple electronic circuit converts alternating current to direct current, and power electronic circuit can increase or decrease the input voltage.
Objectives. At the end of this session, you will be able to construct the full wave rectifier using simulation software and construct the chopper circuit using simulation software. Introduction to rectifiers. A rectifier is an electrical device comprised of one or more diodes that allow the flow of current only in one direction. It basically converts alternating current into direct current. See the different types of rectifiers. They are half-wave rectifier and full-wave rectifier. Let's see each of these in detail. Half-wave rectifier. The half-wave rectifier is the simplest type of rectifier and consists of a single diode, an AC source, and a load resistor. Full-wave rectifier. Full-wave rectifiers rectify both halves of the input AC waveform, resulting in a smoother DC output compared to half-wave rectifiers. There are two main types of full-wave rectifiers: center-tapped and bridge rectifiers. Now let's see what are chopper circuits. Chopper circuits, also known as DC to DC converters or switch mode power supplies, are electronic circuits used to control and regulate the conversion of DC voltage from one level to another. Types of chopper circuits: step-down chopper or buck converter and step-up chopper or boost converter. Let's see each in detail. Step-down chopper. In a buck converter, the output voltage is lower than the input voltage. Step-up chopper. A boost converter increases the output voltage above the input voltage. Next, we will look at the construction of a simple electronic circuit and power electronic circuit using simulation software. For this, you will need the following tools and equipment such as personal computer and simulation software installed in the personal computer. Now let's construct the full wave rectifier using simulation software. First, open the simulation software that is pre-installed in the PC. To create a new file, click on New Schematic. Now let's place the required components for the construction of full wave rectifier. For that, we need inductors, diode, resistors, and a voltage source. For placing the component on the schematic, select the component on the menu bar. Tip: for placing component, you can type P on your keyboard. In the search box, type voltage and click on Place the component on schematic. Next, search for the inductors in the components dialog box for that type of inductor and place it on the schematic. Here, we need 3 inductors. So repeat the steps again. And click Ctrl+R to reverse. Next, search for the diode in the components menu or simply press D as keyboard shortcut. Repeat the same for the rest 2 diodes. Next, search for the resistor in the components menu or simply press R as keyboard shortcut. Now to place ground, simply press G on the keyboard and place it on the schematic. After placing all the required components on the schematic, begin wiring between the components. For wiring, go to the menu and select option Wire. Tip: for wiring shortcut, click W to start wiring. Now wire up according to the circuit diagram and connect to the ground. Next, we need to fix the voltage specifications. For that, first right-click on the voltage and click on Advanced. Select the sine mode for generating the input signal. Now fill the columns. Here, we choose the offset value as 0 volt, amplitude as 230 volt, and frequency as 50 Hz. Now select the series resistance value as 0.1 milliohm. Next, we need to fix the inductance value. For that, first right-click on the inductor. Now fix the first inductance value as 1 millihenry and click OK. Now again right-click on the second inductor and fix its value to 40 microhenry and click OK. Right-click on the inductor and fix its value to 40 microhenry and click OK. Next, we need to fix the resistance value. For that, first right-click on the resistor. Now fix the first resistance value as 10 kilo ohm and click OK. Now we need to fix the diode specification. For that, first right-click on the diode and select the option as Pick a new diode. Then, a drop-down list appears and select the diode 1N4148 from the list and click OK. Repeat the same for the next diode also. Now we need to specify the coupling coefficient. For that, first click on the Edit option and then select the SPICE directive. Then type KL1, L2, L3, 1, where K is the coupling coefficient, L1, L2 and L3 are the labels of the inductors, and 1 represents the value of the coupling coefficient. Before testing the circuit, make sure that all the connections are correct. Now let's test the circuit. For testing, first we need to determine the duration of the simulation. For that, first click on the Configure Analysis icon or press A as keyboard shortcut. A dialog box appears. In that, select Transient and type the stop time. Here, we set the stop time as 0.2 to see 5 cycles. That is, number of cycles divided by frequency is equal to stop time. Now we can run the simulation. For that, click on the Run icon or press Alt plus R as keyboard shortcut. Now we can plot the input and output waveforms. For plotting the input waveform, place the cursor on the wire connecting the input voltage. The input waveform is getting plotted. Now we can plot the output waveform on a separate plot plane. For that, first right-click on the mouse and select the option as Add a plot plane below. Now to plot the output waveform, click on the wire connecting the resistor as diode as shown. The output waveform is getting plotted. Now let's construct a power electronic circuit. Here, we will construct a step-down chopper circuit or buck converter using the simulation software. First, construct the chopper circuit according to the circuit diagram given. Place all the components and wire accordingly. Wire according to the circuit diagram. Now we assign values for each component in the circuit. Input voltage V1 is equal to 50 volts and click OK. Inductance is equal to 50 microhenry and click OK. Capacitance is equal to 100 microfarad and click OK. Resistance is equal to 1 ohm and click OK. Next, we need to fix the voltage specifications. For that, first right-click on Voltage and click on Advanced. Select the Pulse mode. Now fill the columns. Set the initial voltage as 0 volt. V on voltage is equal to 12 since we are using gate source voltage. Most MOSFETs can accept voltages between 5 to 20 volt. Time delay is equal to 0. Set the rise and fall time as 1 nanosecond. Time on is equal to 0.3 multiplied by 10 microseconds. Time period is equal to 10 microseconds. And click OK. Now we need to fix the diode specification. For that, first right-click on the diode and select the option as Pick a new diode. Then a drop-down list appears and select the diode MBRS1100 from the list and click OK. Now we need to fix the MOSFET specification. For that, first right-click on the MOSFET and select the option Pick a new MOSFET. Then a drop-down list appears. Select the preferred MOSFET from the list and click OK. Now let's test the circuit. For testing, first we need to determine the duration of the simulation. For that, first click on the Configure Analysis icon or press A as keyboard shortcut. A dialog box appears. In that, select Transient and type the stop time. Here, we will set the stop time as 0.15 milliseconds. And click OK. Now we can run the simulation. For that, click on Run icon or press Alt+R as keyboard shortcut. Now we can plot the input and output waveforms. For plotting the input waveform, place the cursor on the wire connecting the input voltage. The input waveform is getting plotted. Now we can plot the output waveform on a separate plot plane. For that, first right-click on the mouse and select the option as Add a plot plane below. The output waveform is getting plotted.
This brings us to the end of this session. In this session, we have learned to construct the simple electronic circuit using the simulation software and construct the power electronic circuit using the simulation software. Thank you for watching. We will see you in the next session. Hello and welcome to this session. In today's session, we will delve into electronic lamp dimmer circuits, implementing them in Proteus software. By simulating triac control and user input, we will replicate adjustable brightness for lamps virtually, facilitating circuit design and testing.
Objectives. At the end of this session, you will be able to construct an electronic lamp dimmer circuit using simulation software. Electronic lamp dimmer circuit. An electronic lamp dimmer circuit is a device used to control the brightness of a lamp, typically an incandescent lamp or a dimmable LED lamp using electronic components. Let's now see the basic working principle behind this. The basic principle behind electronic lamp dimmers involves controlling the amount of power delivered to the lamp, thereby varying its brightness. This is commonly achieved by adjusting the conduction angle of a switching device such as a triac in response to user input. Let's delve into the key components needed for constructing an electronic lamp dimmer circuit. Triac, example BT136. Diac, example DB3. Inductor, rheostat, potentiometer, resistor, and capacitor. Let's see each of these components in detail. Triac. The triac is a semiconductor device that acts as bidirectional switch capable of conducting current in both directions when triggered. It consists of three terminals: main terminal 1 MT1, main terminal 2 MT2, and a gate G. The triac can be triggered into conduction by applying a gate current, typically through a pulse of voltage source. It is commonly used in AC power control applications such as lamp dimmers, motor speed control, and AC power switches. Diac. The diac is a bidirectional semiconductor device that is commonly used as a trigger device for triacs. It has two terminals and is designed to conduct when a certain voltage threshold is reached. The diac is often used in conjunction with a resistor and capacitor to form a triggering network that provides the necessary voltage to trigger the triac. Inductor. An inductor is a passive electronic component that stores energy in a magnetic field when current flows through it. In lamp dimmer circuits, an inductor is often used to smooth out the voltage across the lamp, reducing flicker and improving performance. It helps to maintain a more stable voltage supply to the lamp by reducing fluctuations caused by variations in the AC power source. Rheostat or potentiometer. A rheostat, also known as a variable resistor or potentiometer, is a three-terminal resistor with a sliding or rotating contact. It is used to control the current flow in a circuit by varying its resistance. In lamp dimmer circuits, a rheostat is typically connected in series with the triac to adjust the amount of current flowing through the lamp, thereby controlling its brightness. Resistor. A resistor is a passive two-terminal electrical component that opposes the flow of current. In lamp dimmer circuits, a resistor is often used to limit the current flowing through a diac and protect it from damage. It is typically connected in series with the diac to ensure proper operation and prevent excessive current flow. Capacitor. A capacitor is a passive electronic component that stores energy in an electric field when voltage is applied across its terminals. In lamp dimmer circuits, a capacitor can be optionally used for noise filtering purposes. It helps to smooth out fluctuations in the circuit's voltage and reduce electromagnetic interference or EMI. Next, let's understand the working of an electric lamp dimmer circuit. When AC power is applied, the voltage passes through the triac, which acts as a switch. The diac connected in series with a resistor and capacitor provides the triggering signal to the triac when the voltage across it reaches a certain threshold. The triac then conducts, allowing current to flow through the lamp. The inductor helps smooth out the voltage across the lamp, reducing flicker and improving performance. The rheostat connected in series with the triac allows the user to adjust the brightness of the lamp by varying the resistance. By adjusting the rheostat, the amount of current flowing through the lamp changes, thereby adjusting its brightness. Next, let's see the tools and equipment needed to construct the electronic lamp dimmer circuit. For this, you will need the following tools and equipment such as personal computer and simulation software installed in the personal computer. Now let's construct the electronic lamp dimmer circuit using the simulation software. First, open the simulation software that is pre-installed in the PC. Before opening the application, run as administrator for accessing all the libraries. Click on New Project to construct the circuit diagram. Name the project. Here it is saved as Electronic Lamp Dimmer. Click Next to proceed. Select Create a Schematic and continue with the default mode. Click Next to proceed. After selecting all the layouts, click Finish. Before placing all components, refer to the circuit diagram. Now we can place each component on the schematic according to the circuit diagram. For placing each component, click P as keyboard shortcut. Type the components. This includes resistors and click OK. Right-click to place the previous component. Capacitors and click OK. Right-click to place the previous component. Lamp and click OK. Variable resistor or potentiometer and click OK. Voltage source and select the V sign in the library. and click OK. Inductor and click OK. Diac and click OK. Triac and click OK. Switch and click OK. Fuse and click OK. Align each component on the schematic. Now, after placing each component, we can wire up the circuit. Place the cursor near the component to start wiring. Now, for giving the values for each component, first select the components. Right-click and select Edit Properties and assign the values. Or press Ctrl+E after selecting the object as the keyboard shortcut. Repeat the same process for all the components. Fix the value of each component as follows. R1 is equal to 10 kilo ohms and click OK. R2 is equal to 180 ohms and click OK. R3 is equal to 470 kilo ohms and click OK. Inductor L2 is equal to 1 millihenry. And click OK. Capacitors C1 is equal to 0.1 microfarad. And click OK. C2 is equal to 0.1 microfarad. And click OK. C3 is equal to 0.1 microfarad. And click OK. C4 is equal to 1 microfarad. And click OK. Variable resistor is equal to 250 kilo ohm. And click OK. Fuse is equal to 1 ampere. Remember to tick in the dialog box of Attach Hierarchy module and click OK. Next, we need to fix the voltage specifications. Change from Hide All to Show All. Set DC offset as 0 volt. Set amplitude to 230 volt and frequency to 50 Hz and click OK. Now we can test the circuit. Before testing, make sure all the connections are properly done. For testing, click on the play button on the bottom left. Now close the switch and observe the brightness of the lamp as we are adjusting the rheostat. On increasing the resistance value, the lamp will become more brighter as we connected the rheostat in parallel.
This brings us to the end of the session. In this session, we have learned to construct an electronic lamp dimmer circuit using simulation software. Thank you for watching. We will see you in the next session. Hello and welcome to this session. Today, we will come with a very interesting topic to be discussed, that is configuring the input-output pins of 8051 microcontroller and execution of a simple program by using them.
Objectives. At the end of this session, you will be able to identify the port pins in an 8051 microcontroller and enter the program in the microcontroller kit and execute it. Let's first see what a microcontroller is. A microcontroller is a small and low-cost microcomputer which is designed to perform the specific tasks of embedded systems. The general microcontroller consists of the processor, the memory which includes RAM, ROM, EEPROM, serial ports, peripherals like timers, counters, etc. Now let's look into the pin description of 8051 microcontroller. Pins 1 to 8. These pins are known as port 1. They serve as an input or output port. Pin 9. It is a reset pin which is used to reset the microcontroller to its initial values. Pins 10 to 17. These pins are known as port 3. RxD pin or receive data. Function. The RxD pin is used for serial communication to receive data from an external device. TXD or transmit data pin. Function. The TXD pin is used for serial communication to transmit data to an external device. INT or external interrupt pin. Function. The INT pin is used to receive external interruptions from peripheral devices or sensors. T0 or timer 0 pin. Function. T0 is one of the timers in the 8051 microcontrollers used for timing and counting applications. T1 or timer 1 pin. Function. T1 is another timer in the 8051 microcontrollers used for timing and counting purposes. Write and read signals. Function. These signals are typically used for interfacing with external memory or peripherals. Pins 18 and 19. These pins are used for interfacing an external crystal to get the system clock. Pin 20. This pin acts as a ground or negative power supply to the circuit. Pins 21 to 28. These pins are known as port 2. It serves as an input or output port. Pin 29. This is PSEN pin, which stands for Program Store Enable. Pin 30. This is ALE pin, which stands for Address Latch Enable. Pin 31. This is EA pin, which stands for External Access Input. Pins 32 to 39. These pins are known as port 0. It serves as input or output port. Pin 40. This pin is used to provide power supply to the circuit, typically plus 5 volt. Next, we will look at the tools, equipment and materials needed to demonstrate the port pins of the controller and configure the ports for input and output operation. For this, you will need the following: monitor or laptop 1 number, microcontroller kit 1 number, USB cable 1 number, FRC cable 2 numbers, FlashMagic software, and Keel Microvision software. Now we will run the program using the software called Keel Microvision software. Switch on the computer and open the Keel Microvision software. Now let's enter the program in the Keel software. Once you have opened the software, click on Project and select New Microvision Project. Open a new folder here and name it as 8051 microcontroller, where we write a program. Create the file name as per the project. Here, it is named as Input-Output Configuration. Click Save to proceed. A tab pop-up appears to select the microcontroller. Here, we are using the 8051 microcontroller. Select AT89C51 from the database and click OK. Click No for the start file. On the left side of the screen, a tab called Project appears. Click on the plus beside Target 1. Now Source Group opens. Right-click on Source Group 1 and select Add New Item to Group Source Group 1. Select the ASM file since we are writing the program in assembly language. Name the file here. It is named as Input-Output Configuration. Click on Add to add it on to the Source Group 1. Now start entering the program in the .asm file created. ORG00H sets the origin memory address to 00H. Define a label named L1 to create a loop for the program. MOVA P1 is moving the value of the port 1 or P1 to the accumulator A. This port acts as an input port for the program. Now type MOV P2A to move the value from the accumulator to port 2 or P2. Now type SJMP L1. This line helps us to jump back to the label L1 that we have created. This creates an infinite loop. Now type END to end the program. Now navigate to the target and right-click and select the options for the target 1. Change frequency to 11.052 MHz. Select the box of the Use on Chip ROM. Now go to Menu and select the output. Enter the hex file name in the name of executable. Here it is Input and Output Configuration. Select the box of Create Hex File and click OK to continue. Navigate to the menu and select Translate and check whether there is any error or warnings. In the build output, it will show the number of errors and warnings. Now next to Translate, there is an icon named and click on the build target. In the build output, it will be displayed Creating Hex File from Input-Output Port Configuration. Input-Output Port Configuration, 0 errors, 0 warnings. Turn on the microcontroller kit after entering the program in the software. Now connect the laptop to the microcontroller kit using USB cable. Connect one end of the cable to the laptop and other end to the microcontroller kit. Now click Windows on the keyboard and type FlashMagic to burn the code. Now in step 1, select the microcontroller. The microcontroller specification will vary from kit to kit. Here, we are using 89V5-1RD2. Now for selecting the COM port, click on Windows and type Device Manager. Navigate to ports, COM and LPT and check the port number. Here, it was COM20. Now open FlashMagic and select the COM port as COM20. It varies from kit to kit. Make sure the COM port is No before selecting the COM port. Select the baud rate as 9600 and interface as None, ISP. Now navigate to the options and click on the Advanced options. Go to Hardware Configurations and deselect the USE DTR to control RST. Click on the box of Erase All Flash to erase all the programs previously done in the kit. Now go to Step 3 Firmware and browse the hex file created and select the hex file. Navigate to Step 5 and click on Start. Now click on the Reset button in the microcontroller kit to dump the program into the kit. Connect the ports according to the program. Locate the ports, switch and LED in the kit. Use FRC cables female to female for connecting the ports. Here, port 1 is connected to the switch and port 2 is connected to the LED. Now click on the Reset button again to burn the program. Now toggle the switches to high and low to see the output in the microcontroller kit in the form of LED. When the toggle switch is set to high, the LED will be high, and when the switch is set to low, the LED will be low.
This brings us to the end of the session. In this session, we have learned to identify the port pins in 8051 microcontroller and enter the program in the microcontroller kit and execute it. Thank you for watching. We will see you in the next session. Hello and welcome to the session. In today's session, we will explore the fascinating world of temperature measurement sensors. Understanding the principles and applications of different temperature sensors is essential for ensuring accuracy, reliability, and safety in countless processes and systems.
Objectives. At the end of this session, you will be able to identify the different types of temperature sensors such as RTDs or resistance temperature detectors, temperature sensor ICs, thermocouples, platinum resistance sensors, thermistors, and thermostat sensors, and identify the different parts of temperature sensors. Let's first review the working principle of temperature sensors. Temperature sensors are designed to detect temperature changes by converting heat energy into electrical energy. They receive input information directly or indirectly from their surroundings and convert them into electrical signals for further processing. This electrical output is then used to operate industrial machinery or equipment to control the temperature regulation. Let's now see the types of temperature sensors. The types of temperature sensors that we will look into are RTDs or resistance temperature detectors, temperature sensor ICs, thermocouples, thermistors, and thermostat sensors. Resistance temperature detectors or RTDs. Resistant temperature detector or RTD is a type of sensor that measures temperature by changes in electrical resistance. This sensor is known for its high accuracy. It can be used for its long service life and is very stable in its functioning. The types of RTDs are wire-wound RTDs, thin film RTDs, and coiled RTDs. Wire-wound RTDs. This type of RTD consists of a coil of fine wire, typically made of platinum, wound around a ceramic or glass core. Wire-wound RTDs offer good stability and accuracy over a wide temperature range. Thin film RTDs. Thin film RTDs use a thin layer of resistive material, usually platinum, deposited onto a ceramic substrate. Thin film RTDs are commonly used in applications requiring fast and accurate temperature measurement. Coiled RTDs. Coiled RTDs consist of a platinum wire wound in a helical coil pattern around a ceramic or glass core. This design provides a larger sensing surface area which can improve the RTD's response time and sensitivity to temperature changes. Applications of RTDs. RTDs are used in air conditioning and refrigeration servicing, food processing, stoves and grills, textile production, plastics processing, and petrochemical processing. Next, let us see temperature ICs. Temperature ICs are specialized components engineered for temperature measurement utilizing semiconductor materials. Essentially, they utilize semiconductor properties to translate temperature changes into measurable electrical signals. There are two main types of temperature ICs: analog output temperature sensors and digital output temperature sensors. Analog output temperature sensors. These sensors produce an output voltage or current that is directly proportional to the temperature. The benefit of this type is its simplicity but may require additional circuitry for calibration and signal processing. Digital output temperature sensors. These sensors convert the measured temperature into a digital signal, usually a binary code. They are more complex than analog sensors but offer greater accuracy, resolution, and ease of use with digital systems. Temperature ICs find widespread application across various fields including in central processing units, CPUs, mobile phones, and industrial settings. They are particularly valuable in environments where precise monitoring of temperature-sensitive components is essential for optimal performance and safety. Let's now see the thermocouple sensor. Thermocouples are sensors used for measuring temperature based on the principle of thermoelectric effect. Thermocouples are widely utilized across various industries and applications, including industrial ovens, food processing, furnace control, and environmental monitoring. There are different types of thermocouples used for different applications with respect to voltage and temperature. Thermocouples don't have an operating voltage themselves. They generate a small voltage output based on the temperature difference between the hot and cold junctions. This voltage is measured by a temperature reader and converted to a temperature reading using a reference table. There are three types of thermocouples: Type J, Type K, and Type T. Type J, they have a temperature range from 0 degrees Celsius to 750 degrees Celsius. This is a common and cost-effective option, but not ideal for high temperatures. Type K, temperature ranges from -200 degrees Celsius to 1250 degrees Celsius. This is the most widely used thermocouple due to its wide temperature range and good corrosion resistance. Type T, its temperature ranges from -250 degrees Celsius to 350 degrees Celsius. This is suited for lower temperature applications and offers good accuracy but has a limited range. Let's now see the thermistor sensor. A thermistor sensor is a type of sensor that utilizes a thermistor, a temperature-sensitive resistor, to measure temperature changes in its surroundings. They include bead type, probe type, disc type, and screw type. Thermistors are made of semiconductor materials such as ceramics or polymers, and their electrical resistance changes significantly with temperature variations. Thermistors offer advantages such as high sensitivity, small size, and low cost, making them versatile sensors in various industries and applications. Thermistors typically operate at low voltages, often in the range of a few volts. Thermistors are available in different types with varying temperature ranges. Common ranges include standard thermistors, typically operate in the range of -55 degrees Celsius to +150 degrees Celsius. High temperature thermistors, they can operate up to +300 degrees Celsius or higher. Low temperature thermistors, they operate in the sub-zero temperature range, sometimes down to -100 degrees Celsius or lower. Thermistors are widely used for temperature measurement and control in various applications including HVAC systems, automotive industry, medical devices, and consumer electronics. Let us look at thermostat sensors used in the geysers. Inside the geyser, there is a wool called glass wool. It is also known as fiberglass insulation. Inside the glass wool, there is a tank made up of stainless steel which helps in storing the water. Downside of this geyser, there are thermostat sensors. Once we open the tank, we can locate the thermostat sensor inside the tank. Thermostat monitors the temperature of the water inside of the geyser tank. When the water temperature falls below a preset level, the thermostat activates the heating element to raise the temperature back to the desired level.
This brings us to the end of this session. In this session, we have learned to identify the different types of temperature sensors such as RTDs or resistance temperature detectors, temperature sensor ICs, thermocouples, platinum resistance sensors and thermostat sensors, and identify the different parts of temperature sensors. Thank you for watching. We will see you in the next session. Hello and welcome to this session. Today, we will go into the fascinating world of proximity sensors that play a big role in our everyday lives. Join us as we uncover proximity sensors that enable seamless interactions with our devices.
Objectives. At the end of this session, you will be able to identify proximity sensors and list the types of proximity sensors and their applications. Proximity sensors. These sensors work without making direct contact with an object. It can identify its presence. It makes use of sound, light, and electromagnetic waves to determine if objects are present or not. There are numerous varieties, each suitable for environments and applications. The types of proximity sensors are inductive, capacitive, and photoelectric. Inductive proximity sensor. An inductive proximity sensor is a non-contact device that detects metal targets using electromagnetic energy. Mainly, these are used for the detection of metallic objects. Inductive proximity sensors are available in both AC and DC versions. They have 2, 3, and 4-wire configuration. Let us see what is meant by 2-wire configuration and its applications. Sensors with 2-wire function. 2-wire inductive proximity sensors are non-contact devices used to detect the presence or absence of metallic objects in proximity. They operate on the principle of electromagnetic induction, where a change in the magnetic field causes an induced current in a nearby metallic object. The sensors consist of an oscillator, a detection coil, and signal processing circuitry, all housed within a compact rugged enclosure. Applications of the 2-wire function. 2-wire inductive proximity sensors can be utilized in various industries and applications such as assembly lines, conveyor systems, and automotive manufacturing. Position detection. In industrial automation, 2-wire sensors are commonly used to detect the position of machine components, ensuring that processes run smoothly and efficiently. Object counting. Sensors can be installed along conveyor systems to count the number of items that pass through, providing valuable data for production monitoring and inventory management. Safety applications. 2-wire inductive proximity sensors can be used as safety devices to detect when a metallic object, such as a person wearing a metal safety badge, enters a hazardous area. PNP and NPN sensor. These sensors consist of a proximity sensor circuit and PNP or NPN transistor circuit. The purpose of the proximity sensor circuit is to determine or detect any nearby object. When the sensor circuit detects an object, it sends an output high signal to the transistor circuit. The transistor-based circuit may use PNP or NPN transistors, and it depends on the applications. The sensor is used for PNP and NPN has nothing to do with whether the sensor is normally open or closed. That means a PNP sensor may be either normally open or closed. Likewise, the NPN sensor can also be normally open or closed. 3-wire PNP proximity sensor. A 3-wire PNP proximity sensor consists of 3 wires in which the brown wire is used to connect the positive voltage, the blue wire is used to connect the negative voltage or the ground, and the black wire is the sensor signal output wire. We know that PNP transistor is used for positive switching. The PNP transistor is installed between the positive voltage wire and sensor signal output wire. As negative voltage will be common between sensor and load, connect the voltage wire to sensor and the load. Signal output wire of the sensor is connected to the input of the load. A load can be any device that sensor powers, like a lamp, pneumatic valve, relay, or PLC. In this circuit, let's consider the bulb as load, which needs to glow when a metal object is detected. When PNP proximity sensor doesn't detect any object, the output pin will be low, and so the transistor and the bulb will be off. When the PNP proximity sensor detects a metal object, it emits the voltage almost nearly the same as the voltage fed into the positive voltage pin, and hence the transistor will be on and the bulb will be on. Now let us see how to identify the sensor, whether it is PNP or NPN. Both NPN and PNP sensors typically have 3 wires: power supply, ground, and output signal. The key difference lies in how the output signal operates. NPN or sinking. In its inactive state, the output signal will be at a high voltage level. When the sensor is activated, the output acts like a switch and completes the circuit by sinking the current to ground. PNP or sourcing. In its inactive state, the output signal is at a low voltage level. When activated, the sensor acts like a switch, providing current from the power supply to the output signal wire. Next, let's look at capacitive transducers. Capacitive sensors are a type of sensor that uses changes in capacitance to detect objects. Capacitance is the ability of a pair of conductors separated by an insulator to store electrical energy. When an object comes near a capacitive sensor, it changes the capacitance between the sensor's electrodes. This change in capacitance can be used to detect the presence, absence, or other properties of the object. Proximity sensors. These are the most common types of capacitive sensor. They are used to detect the presence or absence of an object without making physical contact. Proximity sensors are often used in industrial automation applications such as assembly lines and robotics. Typically, proximity sensors operate at a voltage range of 5 to 24 volts DC. Pressure sensors. These sensors are used to measure pressure. They can be used in various applications such as automotive airbags, medical devices, and weather monitoring stations. Pressure sensors typically operate at a voltage range of 5 to 15 volts DC. Humidity sensors. These sensors are used to measure humidity. They are often used in applications such as HVAC systems, greenhouses, and weather monitoring stations. Humidity sensors typically operate at a voltage range of 3.3 to 5 volts DC. Touch screens. Touch screens are a type of human-machine interface, HMI, that uses capacitive sensing to detect the touch of a finger or other object. Touch screens are used in various devices such as smartphones, tablets, and laptops. Touch screens typically operate at a voltage range of 3.3 to 5 volts DC. Let's discuss about photoelectric sensors. Photoelectric sensors are devices that use a light source, usually infrared or visible light, and a photoelectric receiver to detect the presence, absence, or other characteristics of an object. They are widely used in industrial automation for various applications. Through beam sensors. These sensors consist of a separate emitter and receiver unit. They work by detecting an interruption in the light beam between the emitter and receiver. Their operating voltage typically ranges from 5 to 24 volts DC. Retroreflective sensors. These sensors have both the emitter and receiver housed in the same unit. They work by emitting a light beam that strikes a reflector and bounces back to the receiver. The presence of an object in the path of the light beam interrupts the reflected beam and triggers the sensor. Their operating voltage typically ranges from 5 to 24 volts DC. Fiber optic sensors. These sensors use fiber optic cables to transmit and receive light. They are ideal for applications in harsh environments or where the sensor head needs to be remote from the control unit. Their operating voltage typically ranges from 5 to 24 volts DC.
This brings us to the end of this session. In this session, we have learned to identify proximity sensors and types of proximity sensors and their applications. Thank you for watching. We will see you in the next session.
Today I'll be giving a brief introduction and overview of points of quality inspection of various construction materials being used in MES. First and the foremost material which is required for any construction activity is the building storage material, primarily the cement and the steel. The cement bags should be stored properly in godowns with overhead cover and with on proper dunnage.